Okay, welcome to the third lecture of graph theory. In the last class, we had discussed Hall's theorem and its proof. Now, we will see another proof of Hall's theorem. Before that, let me remind you what Hall's theorem was. So, it is about a bipartite graph. So, this is a bipartite graph. This set is A, this set is B. Now, Hall's theorem says that if Hall's condition is valid for this bipartite graph, then there will be a matching of A. That means, there will be a matching which matches all the vertices of A. So, what is Hall's condition? Hall's condition says if you take any subset S of A here, you can take any subset of S of A. There are 2 raised to A possible subsets, any subset of A if you consider, and count the number of neighbors that S has. The neighbors means the vertices of B which has at least one connection to S. If you count this set, and if it so happens that the number you get, the number of neighbors here is greater than or equal to the cardinality of S. If this is true, then we say that the Hall's condition is correct, satisfied this paper. Hall's theorem says if Hall's condition is satisfied, then there will be a matching of cardinality A in this thing, cardinality A in this set, in this bipartite graph. Now, last class we proved this theorem using a theorem which we had already proved before that, which was the Koenig's theorem. Koenig's theorem was about the vertex cover and the cardinality of the minimum vertex cover and the cardinality of the maximum matching in the bipartite graph. We used that to deduce Hall's theorem in the last class. Here there is a direct proof. So, we will go through the proof. So, what we are going to do is to go suppose it is not go by contradiction, suppose this theorem is not true, that means the Hall's condition is valid, but we do not have a matching that matches every vertex of A. In other words, there exists at least one vertex of A which is unmatched. Let us call it A. So, our plan is to construct a sequence of vertices, say A0, P1, A1, P2, A2 like that. So, A0 from the side A which is unmatched, B1 from the side B which is matched, which we will make sure that it is going to be matched, then A1 from the side A, then from B2 from the other side, A2 from this side, like a sequence of vertices which are distinct, right. That means, we will not repeat the vertices in this sequence, and show that we can get a never ending sequence, which is definitely not possible, because only there are finite number of vertices in our graph. Therefore, that will lead to a contradiction. So, how we are going to do this thing, I will explain. Consider this bipartite graph where the Hall's condition is satisfied. We consider the maximum matching in this bipartite graph now. So, let us mark the edges of the maximum matching, the biggest matching possible. So, let us say these are the vertices which got matched from this side, these are the vertices which got matched from this side. Now, because we have assumed that the Hall's theorem is not true for this graph, that means, the Hall's condition is satisfied, still there is no matching which matches all the vertices of A, there should be some vertices here, right. There can be some vertices here also unmatched. These are the unmatched vertices, these are the unmatched vertices on the A side. Now, what we are going to do is to show a contradiction. We told that we picked up an unmatched vertex first. Let me call this A0. Now, my plan is to find a vertex which I will call B1 on the B side. Somewhere here on this side I want to find a vertex B1, right. So, but the essential condition I am looking for, when I am looking for B1, I want to make sure that it is a neighbor of A0. So, they should, I am searching for a vertex here which is a neighbor of A0, and the question first is it possible to pick up B1 here such that B1 is a neighbor of A0? It is not possible to find anything in this collection which is the unmatched vertices of B, anything in this collection which is the unmatched vertices of B, because if there is an edge like this, definitely we could have added it to the existing matching and then we would have got a bigger matching. So, that is not possible, right. So, what we can say is, so there will not be any vertex of that sort. Now, so then is it possible that there is no neighbor of A1 at all in this B1? That means we cannot find a vertex B1 on this side, right. That is also not correct, because since Hall's condition is correct, this vertex A0 should have a neighbor somewhere, this vertex A0 should have a neighbor somewhere here on this side. Let us say, as we have told, any neighbor of A0 has to be in the matched in this collection only. It is not possible to have in a neighbor of A0 in the unmatched, among the unmatched vertices. Let us say this is B1, we pick up one. So, as you can remember, the Hall's condition says that if you select any set of vertices, it should have at least the number of neighbors it has on the other side should be at least as much as the cardinality of that vertex. So, that of that set we are considering. For instance, if you had considered the singleton set, then there will be at least one neighbor. For instance, if there is no neighbor, Hall's condition will not be satisfied for that singleton set. This singleton set will violate it, right. Now, so let us pick up therefore this vertex B1 and write A0 comma B1 sequence. Now, as soon as we got this B1, because we know that this is a matched vertex, so we can take the partner of it on this side, partner of this on this side. So, let us say this is A1, let us call this A1. So, so that A1 will be the next vertex here. Now, we have selected A0 this one and A1 on this side and B1 on this side, right. Now, our idea is to find out a vertex on the B side such that that vertex is a neighbor of at least A0 or A1, one of them, maybe both of them. So, a neighbor on the B side, which I will call B2 later now, such that B2 is a neighbor of either A0 or A1. So, how will I do that? So, first question is it possible to have such at least one neighbor for A0 and A1 together on the other side, which is not B1. So, if that is not true, B1 is the only neighbor of A0 and A1 together, then Hall's condition will be violated. Why? Because if you consider this set of two elements A0 and A1, then according to Hall's condition it should have at least two neighbors on the other side. So, if B1 is the only neighbor that A0 and A1 together has on the other side, then it will definitely violate the Hall's condition. Therefore, there should be one more vertex on the other side, which is a neighbor. So, let us call it B2. Let us call it B2. let us call it B2. Then now the issue is, where is this B2? Is this B2 an unmatched vertex here or a matched vertex here? Can it be an unmatched vertex? Is it possible that our B2 is in this set? That means, can B2 sit here instead of here? So, is it possible to have B2 there instead of here? So, but we see that if B2 is here, then suppose B2, we see that B2 is connected to either A0 or A1. As we have already told, it is not possible to have a connection between B2 and A1 A0, because if say this connection was there, if this connection was there, then already we can make the matching bigger by adding this green edge to the already existing these red edges. So, therefore, that is not possible. So, what we see is we can connect, so possibly B2 is a neighbor of A1, possibly B2 is a neighbor of A1, suppose it is like this, say suppose B2 is a neighbor of A1, is it possible? So, in that case what we see is, say follow this path. So, from A0 we can reach B1, and from here we can come like this to A1, and then from here we can reach here, right. So, this is definitely an alternating path. In fact, if you remember what we defined last time, it is called an augmenting path. Why is it an augmenting path? It starts from an unmatched vertex on the A side, it reaches it follows an unmatched edge and reaches a matched vertex on the B side, comes then travels via a matching edge, then travels by an unmatched edge and reaches the unmatched vertex on the B side. So, this is an alternating path, because it starts on an unmatched vertex on the A side and reaches an unmatched vertex on the B side, and by traversing unmatched edge and then matched edge, unmatched edge, matched edge, like that. So, but then we know that if there is an augmenting path, the matching we have already considered, this red edges, that is not a maximum matching. Why? Because we could have replaced this matching edge by this two other edges in the augmenting path. We could have replaced instead of this, we could have replaced this thing. So, then these vertices will also get matched, these new two vertices also will get matched. So, we will get a bigger matching here using this augmenting path. So, therefore, it is not possible to have B2 outside. So, B2, so the inference is that B2 is also somewhere in this area, that means B2 also should be among the matched vertices of B. So, let us erase the unnecessary things now. So, all this right. So, this is our original matching. Now, what we have seen is we have a B2 here on the B side. So, I can write B2 and B2 is a matched vertex, therefore, as its partner on this A side, say it will be called A2, and then that will be added to the next one. Now, we will again ask the same question, can I find a B3 now, right? What are the properties which B3 requires? B3 wants, we want B3 to be a neighbor of either A0, A1 or A2, A0, A1 or A2, right, in such a way that means a neighbor of this 3 element set, right. Will we get a B3? Yes, because the Hall's condition is true, we have to get one B3 which is other than B1 and B2. Why? Because if B1 and B2 are the only neighbors of A0, A2, A1, A2, then Hall's condition is violated, because there are 3 elements in this set, there are only 2 elements in the 2 vertices in the neighborhood of that. So, there should be at least 3, there should be one more, and so let it be B3, but this neighbor, again the question is, can it be unmatched? So, if it is unmatched, as we argued before, it will give us a augmenting path. Why? Because depending on B3 is, if B3 is connected to A0, we immediately have a contradiction. If B3 is connected to A1, then as before we had a augmenting path like that of A0 to B1, B1 to A1 and A1 to B3. If B3 was connected to A2, then we have an augmenting path like A0 to B1, B1 to A1 and A1 to B2 and B2 to A2 and then A2 to B3. So, that will be a slightly longer augmenting path. Depending on which vertex it is connected, we will get a augmenting path, because every vertex we select on the A side, that means A0, A1, A2 etc., will all end in one alternating path. It will be ending in at least one alternating path, and then if it is this B3 is connected to the new vertex on the other side is connected to that vertex, this is alternating path can be extended to an augmenting path. And once we get an augmenting path, we know that we will get a bigger matching by replacing the red edges in them by the other edges, right, as we already discussed. So, that is why we can always get a new BI. So, going back to our slides. So, we will see that once we get A0, A1 up to AI, we can always find a BI plus 1 such that BI plus 1 is a neighbor of one of these vertices A0, A1 or A2 up to AI. That is always guaranteed because of the Hall's condition. Now, this BI plus 1 cannot be an unmatched vertex, because if BI plus 1 is an unmatched vertex, then we will end up with an augmenting path, which contradicts the assumption that we have already taken the maximum matching. So, so we can, once we get a BI plus 1, it is a matched vertex, and then we can always get an AI plus 1 by traversing back through that the corresponding matching edge, right. So, its partner BI plus 1's partner on the A side will be AI plus 1. So, it happens, what we see that the sequence will keep on going, it will, we do not see an end to it, right, because there is no reason for it to end. Always we will find BI plus 1, always we will find AI plus 1, all are distinct. How is it possible? It is definitely not possible, because we do not have so many vertices in the graph, it will finish off, right, the matched vertices will finish off at that time, at some point of time. So, therefore, at some point of time we should run out of the matched vertices on the B side, and we will not get a new BI plus 1. But what is the contradiction? It is the only way the contradiction, the only reason for the contradiction is our assumption that we could pick up an A0 to start with, because that is the extra vertex, right. So, that A0 was an unmatched vertex. So, we can infer that we can never pick up an unmatched vertex, that means all the vertices were matched by the maximum matching. That means, we really had a matching of A in the graph. So, that is the inference. So, this is a another proof of Hall's theorem. That means, if the Hall's condition is satisfied, then there will be matching of A in the bipartite graph. Now, the next thing is to see how we can use Hall's theorem to infer some interesting results. For instance, see, when it comes to checking whether the Hall's condition is true or not. So, it will come to verify whether each subset of the A side, that as I mentioned, there are 2 to the power cardinality of A subsets. So, all of them satisfies the Hall's condition, that means the neighborhood is greater than or equal to the cardinality of A. But that is a tedious job. But of course, there are some situations, in some special cases, we can immediately see that the bipartite graph will satisfy the Hall's condition. For instance, one such case is when the bipartite graph is k regular. So, I can remind you what k regular means. K regular means all the vertices of this bipartite graph has degree k, degree equal to k. Degree means the number of edges incident with each vertex is k. So, I assume k greater than or equal to 1, otherwise definitely there will not be any Hall's condition also will not be satisfied, because there will not be any neighbors, right. So, then we want to show that here in for a k regular bipartite graph and k greater than sorry. So, what I meant to say is if k was equal to 0, then definitely there will not be a perfect matching. So, if k is greater than or equal to 1, we want to say that there is a perfect matching. How do I show that? So, it is definitely from, if you want to apply Hall's theorem to do this thing, it is very easy to see that what we have to show is the Hall's condition is true for this any k regular bipartite graph. If the Hall's condition is true, automatically there will be a perfect matching. That is what Hall's theorem says us. So, how do we show that the Hall's condition is true for k regular bipartite graphs? So, to show this thing, so let us take up an example again, a picture let us consider. So, here is the bipartite graph. It is supposed to be a k regular bipartite graph. Now, take an arbitrary subset S of it. Let us say this is an arbitrary subset S of it. Now, I want to show, let us look at the neighborhood of this. Neighborhood of this means I collect all the vertices that is connected to at least one vertex in S. So, all the vertices which is connected to at least one vertex in S. This is what this thing S, and this is called N of S, right, neighborhood of S. Now, I want to show that the cardinality of this N of S is, the cardinality of this N of S is at least as much as S. We want to show that N of S cardinality is, sorry. So, the cardinality of N of S, this is the aim, the cardinality of N of S is greater than or equal to S is what we want to show. This is what we want to show. To show this thing, the technique is to count the number of edges that goes out of S. That means we ask how many edges are such that it has one endpoint in S. Naturally, this can be easily counted. We ask how many edges are going out of one, see this vertex from S, and then another vertex you take. So, like that we can ask, for instance. So, if I mark this, the vertices in this thing. So, this the vertices in this set is this one. So, now I ask how many edges are going out of this, how many edges are going out of this, how many edges are going out of this. So, definitely there are k of them here, there are k of them here, and there are k of them here, and totally definitely cardinality of S into k edges will go out, right. The number of edges you see here will be this much. So, this will be, this many edges will go out. Now, where will these edges go? So, all these edges should go into this set. It may be possible that some vertex here may have an edge going somewhere else, but any edge which is coming from this subset has to reach here. This subset has to reach here. Subset has to reach here. So, that is the this thing. So, but then how many edges can reach here? So, you know that because there are only N of S, cardinality of N of S number of vertices here, and each vertex can accept, or accept means the only at most k edges can come into it, right. So, we know that the only k into N of S edges. So, let us say, so we will say only k into N of S edges can get into it. But then, so definitely this number has to be greater than or equal to this number, because S into k edges has to get into it, and only this many can come into it, right. So, which essentially means that this has to be greater than this. Now, cutting k and k, we get N of S is greater than or equal to S. This is what so we see. So, therefore, for any, since S was selected as an arbitrary set, so therefore, for any set, any subset S of A, we will get this Hall's condition true. So, N of S greater than or equal to S. Therefore, Hall's theorem says there is a perfect matching in the bipartite graph. So, that is what we see. Now, now we will look at another example where we can apply the Hall's theorem. This is another statement which looks a little different, because this is a statement about more general kind of graphs. Say you take any undirected graph. See, there is why do I say undirected graph? It's a usual graph which we were discussing. The kind of graphs we were discussing up to now are undirected graphs. So, I will soon explain what is a directed graph. So, you consider any undirected graph which is 2k regular, that means all the vertices have degree 2k. We want to say that will have a cycle cover. That cycle cover we have already discussed, it is also called 2 factor. That means you can get a collection of cycles. So, let us go here, what is a cycle cover? So, for instance, so you will be able to as I had told you, for instance, so look at this vertex. So, a cycle cover of this graph can be marked like this. See, one cycle, another cycle, all the vertices are to come, have to come in exactly one cycle. We should find out a few cycles, a collection of cycles in the graph such that each vertex of the graph is contained in exactly one cycle. On the other hand, if you had taken a graph like this, so for another example, for instance, if you taken a graph like this, here we cannot find a cycle cover because it is not possible to get this vertex in any cycle, right. It is not possible to get a collection of cycles such that this is in one of them. Or for instance, is it possible to have a cycle cover for this kind of a graph? Is it possible to have a cycle cover for this kind of a graph? So, yeah, so it is, for instance, if you had taken this cycle, then there won't be any cycle. If you had taken any more cycle which I can take, if you had taken this cycle, then who will cover this? So, there are graphs which doesn't have cycle covers. There are graphs which do not have cycle covers. There are graphs which have cycle covers. So, it is also called 2 factor. If you remember, a 2 factor is a subgraph of the given graph which is spanning and 2 regular. A k factor was a subgraph of the given graph which is spanning and k regular. Spanning means it has to contain all the vertices of the given graph, and on top of that it has to be k regular. Then we say that it is a k factor of the given graph. 2 factor is definitely a cycle cover, because if it is a spanning subgraph and 2 regular, then it has to be a collection of cycles. Now, the statement says, if you give me any 2k regular, that means it is a regular graph, but the degree of each vertex is an even number, 2k regular graph, not 0, that means 2k has to be at least 2. It has always got a cycle cover, is what this statement says. How do we go about proving this? So, before getting to the proof of this statement, let us consider some ideas which we will need. One idea is that of a natural way to associate a bipartite graph to a given undirected graph, or also to a directed graph. So, we will consider that. So, suppose just let us take this graph. So, this is a simple graph. So, one way to associate a bipartite graph is like this, to it is like this. So, what I do is this 1, 2, 3, 4 are the vertices of this graph, 1, 2, 3, 4 are the vertices of this graph, and then I will make 2 copies of the vertices of this graph. So, that means 1, 2, 3, 4, again 1 dash, let us say 2 dash, 3 dash, 4 dash, to distinguish, that is another copy. Now, I see that there is an edge here between 1 and 2. So, I will put an edge here between 1 and 2 dash, and also 2 and 1 dash. for one edge here I put two edges, and so I see that between 1 and 3 there is an edge. I put the corresponding edge corresponding to this edge, I will put 1 and 3 dash and 3 and 1 dash. Similarly, there is an edge here between 3 and 4, I will put an edge between 3 and 4 dash and 4 and 3 dash, and here between 2 and 4 there is an edge. So, I will put an edge between 2 and 4 and 4 and 2 here for 2 dash here, right. Now, this is the last edge here between 3 and 2, I will put this 3 and 2 dash edge and 2 and 3 dash edge. This is the bipartite graph which is associated to this thing. This bipartite graph we associate with this graph G is called a double cover. This is the word which we use, double cover of G. Double cover of G. Double cover of G. So, this is a natural way of associating a bipartite graph to a given graph. We just make two copies of the vertices, and corresponding to each edge of the graph we put two edges to the double cover. That means, between I to j, if we see an edge in G, we put I to j dash and j to I dash. This is our strategy, and so this is one concept. And then an interesting thing, for instance, you see that because this is an undirected graph corresponding an edge I to j, we had to put two edges in the bipartite double cover. But if we had started with a directed graph, so what do I mean by a directed graph? Which means that each edge has also got a direction associated with it. So, let us say if this is our graph, so we will also put an arrow, a direction associated. So, this edge is not just this, it is from here to here, that is what we will say, from here to here. Similarly, so we will say this may have a direction like this, this is from here to here. So, if I number it 1, 2, 3, 4. So, it is essentially ordered pairs. In the graph case, undirected graph, though we use the notation of ordered pairs, that is essentially an abuse of notation. In fact, it is an unordered pair, an edge is an unordered pair, while here in directed graph it is really an ordered pair. We can write it as 1, 2, 1 to 2 there is an edge. Similarly, 2 to 3 there is an edge here. Similarly, 1 to 3 there is this edge, right, suppose. So, like that. So, 3 to 4 we can put. So, some directions are associated with each edge. So, like in the graphs we were undirected graphs, we were considering a mostly simple graphs. That means between any two vertices we have only one edge, and also there were no self loops. So, of course, in the directed, because we wanted to avoid the repetition, so to make things simple. So, in the directed case, because there is a direction also, see it is natural to have this, allow this kind of edges also if necessary. That means it is not, this edge is very different, really different from this edge, right, because two endpoints are different, 2, 3 and the other is 3, 2. So, if there is a self loop, you can have this kind of, so there is only one direction, 4 to 4, it will correspond to the pair 4 to 4. So, that is also possible. Now, okay, so this is this will essentially, once you get a directed graph, you can write down the pairs, and that will be a subset of case subset of n to n, subset of v cross v, right. So, therefore, it essentially represents a relation and now coming back to our point. So, we could have constructed, starting from a directed graph also, suppose we take this directed graph, we could have constructed a say double cover of this directed graph also, for instance. So, in that case what we will do is the same trick, but so we will have two copies of the vertex set, say 1, 2, 3, 4, say 1 dash, 2 dash, 3 dash, 4 dash, and 1 2, this is a directed edge, therefore, we will put 1 2 dash, we will not put this edge, we will not put, in the undirected case I will put this also, right. We will just put this here to show that we are only interested in this directed edge. So, the direction is same. So, similarly 2 3 will be marked like 2 3 dash, and 3 4, this will be 3 4 dash, and then 4 1 will be like this, and then 1 3 will be like 1 3 dash. This is the way we will make the corresponding thing. So, here we are not putting 2 edges corresponding to one edge, because one directed edge will translate to one edge in the bipartite graph here. This is the bipartite double cover of this directed graph. Now, so why did we explain all these things? Because see, we were our plan was to make a statement about the existence of a cycle cover in a graph, and we told we are going to prove it using Hall's theorem. So, the Hall's theorem is about bipartite graph. So, we have to, so Hall's theorem is about bipartite graph, Hall's theorem is about perfect matching. Therefore, we have to translate the cycle cover problem to a matching problem. So, therefore, there should be some relation between the cycle cover in the directed graph and also cycle cover in the graph, and then the perfect matching in the bipartite, the corresponding bipartite graph. So, that is why we are constructing this this corresponding bipartite graph, which we called double cover, right. So, what am I going to do? So, let us say there are, if you constructed a bipartite cover of a graph, right, for instance. So, suppose you constructed a bipartite cover of a graph. Suppose you constructed a bipartite cover of a graph. So, and it so happens that, see, this is the graph G, and then we see it is a directed graph, and we see a cycle cover of this graph here, suppose something like this, right. So, this is say 1 2 3 4 5. So, what do we see corresponding to this cycle cover here? So, this 1 2 edge will translate to a 1 2 dash edge here, and 2 3 edge will translate to a 2 3 dash edge here, and then 3 4 edge will translate to a 3 4 dash edge here, and like that. So, this each edge will translate to a mutually disjoint, mutually the edges which are independent here, right, because you can see that any vertex here, say 1 here on the cycle cover. So, I will see there will be there are 2 edges here on the cycle cover which touches, one is an outgoing edge and one is an incoming edge. For instance, this 5 1 edge will come like see 5 1 dash. So, this incoming edge here will translate to a 5 1 edge which is which will touch 1 dash, while the outgoing edge here on this thing will translate to a 1 2 dash edge here, right. Or in other words, if I say this if you consider a vertex here, it has one outgoing edge and one incoming edge. The outgoing edge will be the edge which is incident on that vertex, the copy of that vertex on the A side. The incoming edge will become the edge which is incident on the copy of that vertex on the B side, right. So, therefore, here in the cycle cover, though we see 2 edges touching a given vertex, we will in the corresponding bipartite cover we will see only one edge touching each vertex, essentially because we have made two copies for each vertex. Now again every vertex is there in at least one cycle in the cycle cover. Therefore, corresponding to every vertex we will be having an incoming edge and an outgoing edge. Therefore, so for a vertex I, so we will for the I will have the copy of I in A and B, both of them will see one edge touching them. So all the vertices are touched by one of these edges, and also every vertex is touched by one of these edges, and also what do I say, we get a so therefore we get a perfect matching here, and this is a perfect matching because no two edges will be touching each other. Why is it so? Because given any vertex, only exactly one edge is touching that, therefore two edges will not be able to touch each other. If they are touching each other, then there should be a vertex which has two vertices, two edges incident on it, right. So therefore we see that the cycle cover translates to a perfect matching here. Similarly, once you had constructed the bipartite cover and then look at a perfect matching and then try to see what it means in the original graph, you see that it again gets translated to a cycle cover. Why? Because for instance, if your perfect matching is like this, right, you just have to follow. For instance, this number is 10. 10 goes to say 20, 20 goes to say 18, 18 goes to 50. So like that you can track, and you say that 10, so you will draw an outgoing edge from here to 20, and then you will come to 20 where 20 there is an outgoing here edge from 20 to 18, and then you look for 18 here, and then from 18 to 50 you see an edge. So there is you draw an outgoing edge from 18 to 50. So like that, where will it go and end? Finally, it's clear that it will keep on forming a path. No vertex which is already met will be met again. So clearly it's like that. That's the way we are constructing, and then we will. The only way for it to stop is to come back and hit 10. Right? You will form a cycle sometime. So this will be one cycle, and then we will restart with one of the new. See these all matching edges we have already considered. Start with some of the other matching edges which we haven't yet considered, and we will get another cycle from that. So we will get a collection of cycles corresponding to that. So assuming that we had first got a directed graph, and then we converted it into a double cover. We constructed a double cover from that, and then we are tracking the perfect look at the perfect matching and track the corresponding edges in the original directed graph. We will end up with a cycle cover. So therefore you can see that to prove our theorem, that means given an undirected graph, so the extra condition on the undirected graph is that every degree is equal to 2k, where 2k is some even number of case, 2k is an even number. And so what we can do is we can first give directions to the edges of that undirected graph and make it a directed graph. We say that we can orient the edges, we can give some direction to the edges of each edge of the undirected graph. We get a directed graph, and then from let us call it G dash. And then from there we will okay, what we will do is we will construct the bipartite double cover of that G dash. So first we will give some direction, so how we are going to give directions to the edges is another issue. We are going to explain it later. But the first step is to give direction to the edges of the undirected graph in such a way that it becomes a directed graph now, and from the directed graph we will construct a bipartite double cover. This is the plan. And once we get a bipartite double cover, So, we finally want to prove that there is originally in the original graph there is a cycle cover. Of course, to prove that there is a cycle cover in the original graph, it is definitely enough to prove that there is a directed cycle cover in the directed graph. So, what is a directed cycle cover? A cycle cover, we also insist that a cycle we allow only cycles if we traverse the arrows along the cycle, it should be in the proper direction. It should not be that you enter a vertex and you see the arrow in the coming inward that vertex, right. We should be by following the arrows, you should be able to traverse the cycle. So, we can always look for a directed cycle cover. Of course, directed cycle cover in the corresponding directed graph, when we discard the arrows on the edges, will become a cycle cover in the undirected graph, isn't it. So, now it is, of course, the two questions come. So, how will I prove that in there is a directed cycle cover? Of course, as we see, we have further transformed it to a bipartite double cover of it. So, looking for the cycle cover in this directed graph will be equivalent to looking for a perfect matching in the bipartite cover of it. So, and we know that if this bipartite cover, that bipartite graph is a regular graph, if it is a regular graph, then we can if it is a regular graph, then we can what do we say? So, we can definitely infer that there is a perfect matching. That perfect matching will become a cycle cover in the directed graph, and that will become a cycle cover in the original graph also. That is the trick. So, but then now how do I make sure that there is a perfect matching in the bipartite double cover? Of course, so there is, for that perfect matching to be present, one good thing is this Hall's theorem. So, if we somehow can establish that the Hall's condition is true, then there will be a perfect matching. So, and as we have seen, if it is a k-regular graph, if it is a k-regular bipartite graph, definitely the Hall's condition will be true and there will be a perfect matching. But how can I ensure that this bipartite graph we finally construct is a k-regular graph? Is it possible to guarantee that? To do that, we should see what correspond to the degree of a vertex in this bipartite graph. Clearly, as you can see in this construction, if you take any in the double cover construction, you see in the graph, if you have any vertex with say so many outgoing, suppose some t outgoing edges, then the corresponding vertex in the A side will have t edges incident on it, right, because the outgoing edges become the edges incident on this. Similarly, if there are some t dash incoming edges to that vertex, the corresponding vertex here will have t edges incident on it. So, the degree of the vertices on the A side correspond to the outgoing degree, out degree, we can call it out degree. So, out degree here, that will correspond to this number, and then the in degree here, in degree means incoming, the degree of the number of incoming edges, that is inward edges to that vertex. This will correspond to the degree of the corresponding, the copy of it on the B side, right. So, of course, if you want it regular, then this out degree has to be equal to in degree for each vertex. And if I would, for a given vertex, you know, the total is going to be 2k, because the original graph has only 2k, exactly 2k edges incident on each vertex. So, if out degree equal to in degree, it has to be k and k each, right, out degree equal to in degree equal to k, here it has to be k, here it has to be k, right. So, in other words, the question is this: is it possible to give directions to the edges of the original graph in such a way that the in the directed graph, for each vertex the out degree is equal to in degree, and that is equal to k, because each vertex has total number of incident edges was 2k. Can I make in degree equal to out degree equal to k for each vertex? So, that depends on how we orient the edges of the graph, the original graph. How can we make sure that that will happen? In general, it may not be possible, right? Sometimes, what is the guarantee that you can do that? So, we have to come up with a strategy. So, here the trick we are going to use is to use a concept called Euler tours. What is an Euler tour? The Euler tour means, so you consider a graph. So, here is a graph. So, here is a graph. So, here is a graph. In this graph, so I want to, so you can consider these are all roads. So, these edges correspond to some roads, and then some car is starting a trip from here. So, we travel like this, we reach from this city to this city, and then we take another road, and then we take another road. So, our intention is to somehow traverse each road, but exactly once. That means, we have to go through each road once, but only once. We should not reuse the road. It should, we reached here, now we, if you want to get out of this city, we have to use this road or this road, or we have to go back. That is not allowed, right. So, in this graph you can see that you cannot do that, right. But on the other hand, if you have traveling like this, right. So, no, every road is used, every edge is used, and no edge is reused, it is only used once. So, this kind of a tour is called an Euler tour. That means, it is a traversal of the edges of the graph in such a way that each edge is traversed exactly once. It is traversed once and only once, and you have to reach back where you started. That is why it's a round trip. So, this is called an Euler tour, but the question is, how is it going to help us, right. So, you can see that. So, let us see. So, you draw a graph like this. So, this is our, suppose this is our original graph. So, so let us say, right, this is our original graph, and then I draw this thing. Now, so let me draw an Euler tour here. So, this is the Euler. So, this is the way the car is going, our car, we are traversing the edges. So, now what if I have an Euler tour? So, I claim that this has an Euler tour, I will trace that Euler tour, but along with in the direction in which the car is going, I will give direction to the edges. I will first give direction to this like this, and then I will give direction to this, and then I will give direction to this like this, and then I will give this thing, and then this is the way I am traversing. In whichever direction I am traversing, I also direct the edges as it is covered, because it is only going to be covered once. So, I will give only one direction to the edges. So, this is one way of orienting the edges. So, what you do is you follow the Euler tour, and then as we go through the edge, we will give a direction to that edge which correspond to the direction in which we traverse the edge. See, the good thing about it is, here we can see, if you take any vertex and you imagine that somebody is sitting there and seeing, so the car is coming into the vertex and going out, and again sometime it will come into the vertex and will go out, right. So, therefore, you see that each time the car is getting in, it has to go out also. So, every time it will be using a different road, which means that the in degree has to be equal to out degree. So, if we had followed an Euler tour, because you will come into the vertex and go out, come into the vertex and go out. So, coming in will correspond to one incoming edge, going out correspond to an outgoing edge. So, therefore, if you get an Euler tour in the graph, by following the Euler tour and giving the direction to the edges, in the way we traverse the edges, we can in the direction in which we traverse the edges, we can get the corresponding the kind of orientations that we are looking for, right. So, therefore, that is possible. But the final question is it sure that we have an Euler tour in our graph? So, there is this famous theorem in graph theory that if each vertex of the graph has even degree, that means every vertex of the graph are of even degree, then there is always an Euler tour. This is there in all the textbooks. You can quickly look through that, it is very easy. So, or maybe next time we can just, in the next class we can quickly go through that proof. But so even if you do not do that, it is not a very difficult thing. So, you can quickly think about the proof and find out, and read from any of the preliminary chapters of those reference textbooks, that because our graph was 2k regular. So, each vertex has even degree, namely 2k, and therefore, there is an Euler tour. Now, we follow the Euler tour and give direction to the edges of the graph in the way we traverse, in the direction in which we traverse, and definitely now the orientation is such that the corresponding directed graph, the directed graph which resulted, have incoming degree equal to outgoing degree. Since the total number of edges incident on each vertex was 2k, now the incoming degree equal to outgoing degree has to be equal to k. Now, the corresponding bipartite graph, the double cover, has to be a k regular graph, because the incoming degree will correspond to the degree of the vertex, the copy of the vertex on the B side, and outgoing degree will correspond to the copy of the vertex on the A side. Now, because it is a k regular bipartite graph, there is a perfect matching in that bipartite graph, and this perfect matching, as we have shown, will translate back to a cycle cover in the directed graph. Now, we can discard the directions, we get a cycle cover in the original graph. This is how we have proved it. In this proof, what we have omitted or we have discarded is the proof that if the degree of each vertex in a graph is even, then there is an Euler tour. So, it is easy, you can try to prove it yourself. So, this is the end of this lecture. Thank you.